So welcome to the second lecture in this course on wireless networking. In this lecture, we will examine techniques and methods for determining the communication range and signal strength of wireless signals as they propagate from a transmitter device to a receiver device. Additionally, we will also investigate the methods of estimating the capacity of a wireless channel. So wireless communication systems in our daily life mostly rely on line of sight propagation. We had covered this in the first lecture. And this propagation takes place typically when the frequency of the radio waves is above 30 megahertz. So let's explore how to calculate signal strength and the communication range for the specific propagation mode for radio waves. So when a wireless signal is transmitted from a transmitter device to a receiver device, the strength of the received signal can be estimated by various methods. For line of sight communication, one of the commonly used method is something called Friis transmission equation. So this equation is a mathematical relationship between the received signal power, the gain of the transmitting and receiving antennas, the path loss component, and the distance between the transmitter and receiver. So we are going to discuss some of these terms in detail over the next slides. But the equation can be represented by this formula that is shown on the slide. This equation also has several constants that can be used to account for additional factors that affect the strength of the signal. For example, the environment. So in this formula, we have Fc is the center frequency of the radio waves that are used for communication, and it's typically in hertz. C is the speed of light. D is the distance between the transmitter and the receiver device. Alpha is the path loss component, and G is the antenna gain. And we have separate antenna gains for the transmitting and the receiving device. So let's first look into what the antenna gain as a term means. So we looked at what antennas are. So these are devices that allow you to convert electrical signal into electromagnetic waves and radiate it over the space. So the term antenna gain is a very important concept in Friis transmission equation. And it refers to the increase in the radiated power that an antenna provides in a particular direction when we compare it to an omnidirectional antenna. So an omnidirectional antenna is one that radiates energy equally in all the directions. So sort of like you can assume, or sort of like you can think of the antenna gain to be a measure of the increased radiated power in a specific direction when compared to an omnidirectional antenna. In fact, many of the wireless devices that we have in our house, for example, things like a Wi-Fi router, it usually has an omnidirectional antenna or a array of omnidirectional antenna because it want to sort of like maximize the radiation to reach every corner of the house. So typically antenna gain is measured in this unit called decibels or dB. And the higher the antenna gain, the more the electromagnetic energy is concentrated in a specific direction. In fact, some of the highly directional antenna array can have a gain as high as a few dBs to tens of dB as well. So how do we actually calculate and estimate the antenna gain? It can be sort of like estimated using this formula that we present on the slide, and it's a relationship between the gain of the antenna, its physical size and shape, which is captured in this term called effective area, and again the frequency or the wavelength of the radio waves for which the antenna is designed. So yes, antenna are their gain also depends upon the frequency of the radio waves that you are using it for. So if you take an antenna that is designed for, let's say, 2.4 gigahertz frequency band or a 900 megahertz frequency band, it might not perform as well at lower frequencies or a higher frequency than at which it has been designed for. So while we have looked at the Friis transmission equation and the antenna gain, but there is another equation that is a derivation of Friis transmission equation, and it is one equation that you are going to encounter quite often. And this equation is called free space path loss equation, and it estimates the loss in the strength of signal as it propagates from free space. So when we have these radio waves traveling from a transmitter to receiver, they naturally get attenuated as they propagate over the free space. And this equation sort of like helps you determine how much that loss in the strength of the signal would be as it propagates through the space. But one thing to keep in mind is that this equation only sort of like looks into the losses that occurs just because of the natural propagation of the signal and not because of obstructions or reflections from the environment. So the free space loss equation is also expressed in the units of decibel, and it depends upon some very similar parameters as the Friis equation, except that we don't have transmit and receive power. So the losses that the signal encounters is not dependent upon basically what the strength of the signal is. So in some respect, any signal would sort of like for a particular distance and a particular frequency and a transmit and receive gain would encounter similar losses. So free space path loss is a simple yet a very accurate method of predicting the signal loss in wireless communication systems, and it's very widely used. And there are even calculators that are available online that will help you estimate how much loss a signal would encounter when it is propagating from a transmitter and a receiver. So let's consider an example to look into the free space path loss equation. So let's assume that the transmitter and receiver antenna gain is 2 dB. And this is a very commonly used value for some of the dipole antennas that are used in wireless devices. Now let's fix the distance between the transmitter and the receiver to be 300 meters. So when we plug these values into the free space path loss equation and calculate it for different frequencies, ranging one from the white space frequency band, which is 500 megahertz, to the different ISM bands at 900 megahertz, 2.4 gigahertz, and 5.45 gigahertz, what we find is that the losses become much higher as we basically go higher up in the frequency. And what do we mean when the losses become higher? That means that the signal arriving from the transmitter to receiver while it's traversing a distance of 300 meters is much weaker at higher frequencies than at lower frequencies. So this is an important observation and also explains why many IoT standards and earlier radio systems use lower frequencies for communication. As we had talked about that things like AM radios were operating at even few hundred kilohertz to few megahertz of radio wave frequency. So lower frequencies have much better propagation characteristics. So that means that for the same radiated power, you could reach much higher distances. But of course, there is also a trade-off, as we had seen that the antenna size depends upon the wavelength of the radio waves. So if you have lower frequencies, it has better propagation, but your antennas become much larger, and it can of course be challenged for devices, especially things like, for example, wearable devices like Apple Watch, which requires very small antennas. So you need to also go up in the frequency for you to be able to miniaturize these antennas. So of course, as we have seen that the free space path loss is sensitive to frequency, but there are of course also other facts that have to be considered, as there is always a trade-off between the desired data rate, the distance of communication. Therefore, choosing a frequency band that balances the desired data rate and the distance of communication is essential to minimize the path loss. So let's examine another scenario where we utilize the free space path loss equation to determine the strength of the received signal. So assume that the transmitter emits a wireless signal of strength of 5 dBm, and this is a very realistic strength for IoT devices to radiate because they often need to conserve battery life by transmitting weak signals. So now let's consider the received signal strength for two commonly used IoT frequencies at 900 megahertz and 2.4 gigahertz. Both are ISM band. Using free space path loss, we can calculate that the received signal strength to be about minus 72 dBm and minus 80.5 dBm for the two frequencies. In addition, we can observe that the attenuation is again much higher at the higher frequency. So to further estimate the possible communication range, we also need to consider something called receiver sensitivity, which is the minimum strength of a wireless signal that a radio receiver can actually receive successfully. So typically for radios that are conforming to standards such as Bluetooth, the receiver sensitivity can be between -90 to -100 dBm. So to estimate this range of communication, we can again use the Friis and the free space path loss equation. And I have placed this question on the slide, and I would highly encourage you to sort of like go back and try to solve this question based on what you have learned in the last few slides. So while free space path loss and Friis equation sort of like assumes that there are no abstractions and the transmitter and the receiver are in direct line of sight, but as we had seen earlier that the real world is much more complex, and wireless signals can undergo many different effects, such as, for example, reflection, diffraction, or scattering. We might also encounter, of course, other issues, for example, that we might have, for example, interference from other wireless devices operating on the similar frequency band, or we can also have a multipath because of all these effects, sort of like introducing another path to the wireless signal, and then all of these combined together affects the quality of the link. But despite all of these sort of like complexities that the wireless signal go through in the real world, free space path loss and Friis transmission equations are still a very useful tool for us to understand wireless technologies and standards. So, of course, propagation of actually radio waves also can be affected by their frequency, and actually, if we look at, for example, that the atmosphere can also sort of like affect the strength of the signal. For example, water vapor, oxygen, rain, fog, all of these are present in atmosphere, and they can actually also absorb the signal and attenuate it. And especially, for example, when you are sending radio waves at higher frequencies, they could actually get much more affected by these factors that are present in the environment. For example, the absorption by water is greatest at 22 gigahertz, and the oxygen present in the atmosphere absorbs signals that are above 60 gigahertz. And this is actually an important frequency band because many of the future communication systems like 5G and 6G have started to rely on something called millimeter wave, which actually operates at these higher frequencies. So to account for some of these factors, there is also a term called alpha that is part of free space path loss equation. So here we have this alpha on the we show on the slide, and this can sort of like allow you to factor some of these complexities in the real world to estimate what the received signal strength would be look like. But of course, it just gives you a very rough estimate, and the real values might actually differ from what you are going to calculate using these equations. So thus far, we have examined method of determining the strength of the receive signal and estimating the communication range. In the next part of the lecture, we'll look into determining the capacity or the maximum data rate for wireless communication. That means how much information can you send over a particular part of wireless spectrum. So I go back to this slide that I had shown in one of the first lecture. And we present various wireless standards, their bit rate, and their operating frequencies. And what we can observe is that the IoT standards that operate at lower frequencies also support lower bit rates. And conversely, we can say that the standard with the higher bit rates tend to operate at higher frequencies. So can you actually explain the reason for this particular phenomena? We can actually sort of like get an intuition for it by this very famous wireless capacity theorem that has been devised by Shannon. So this fundamental equation helps us determine the capacity. That means how much information can be carried by a wireless channel. At a very basic level, it defines the capacity of a channel as a relationship between the bandwidth and the signal to noise ratio. So bandwidth can be thought of the amount of spectrum that is occupied by the wireless transmission, while the signal to noise ratio defines the quality of the signal whereas the background noise. So we can sort of like think of that the capacity or the ability of wireless channel to carry information increases as we increase the bandwidth, or we have a better quality signal, which is quite intuitive. So let's try to put this Friis transmission equation and Shannon capacity theorem together. As we had said that the capacity of channel depends on SNR. SNR stands for signal to noise ratio. Let's try to understand this term. So any wireless channel has a level of noise, and we need to be sufficiently stronger than this background level of noise for us to successfully receive wireless communication. And how do we actually ensure that we have good SNR? We can improve the SNR of the signal by increasing the transmitter power. However, usually this is not very straightforward for IoT devices that operate on batteries, because if we increase the transmitter power, it also means that we are sending more energy over the airs, and that means that your batteries would get drained very quickly, and that means you would need to replace batteries more often, which is of course what something that you don't want. So the other the idea that we might consider is that why don't we just increase the bandwidth? But actually it has its own set of challenges. Bandwidth is usually a very scarce quantity. That means how much spectrum that you're occupying for communication, you're also contesting with other devices operating on the same channel. So it's a scarce quantity. That means that you just cannot sort of like take as much bandwidth as you want. But there's also another side effect of increasing the bandwidth, that as you increase the bandwidth, it also increases the noise level on the channel, which affects the SNR level. So while you might get this additional boost because of increase in bandwidth, but it also increases the noise level, which means that the term in the log inside the log actually goes down, which means that your capacity might not scale with the bandwidth as you would have thought of when you were increasing the bandwidth. And of course, we also have this relationship that the wireless communication range decreases as you increase the frequency. We had seen that the losses increase when you are higher up the frequency, and that means that the quality of signal also goes down, which of course also affects the SNR value. So I think there is, as you would see that with many of these wireless systems, there is always this inherent trade-off between different parameters, and you're sort of like trying to find the right match of different parameters for a particular application. And it's not straightforward for us to just say that, okay, you can increase bandwidth or decrease data rate or to sort of like go lower in frequency, because you need to sort of like carefully consider, based on the application, what would be the right set of parameters that will allow you to achieve the metrics for a particular application. So with this, I would end this first part of the lecture, where we looked into how to estimate communication range and how do we use Shannon capacity theorem to figure out how much data can we actually send over a particular part of the wireless spectrum. Thank you very much.